There are a few things that I have created for you by definition, and so I'll run them down, this time quicker than I've ever run them down before. I know that if I choose a coordinate system, I can define positions of objects in my universe. And those positions change, and so the quantity, change quantity that represents changes in position in my universe is the displacement. Displacement, easy to calculate, vector quantity, because that has a magnitude and a direction. And from the displacement, I define the velocity on average. That bar there is the velocity on average. I'm going to need that today. I kept that there for the specific purpose of being precise about what I meant. The average velocity is equal to the displacement delta x divided by time. And that's a very useful definition, and I rearranged it algebraically to say that x is equal to x0 plus the average velocity multiplied by time. I said that that was a rather useful form. I also said that it was an equation that I wasn't going to keep for very long. And today is the day that it's going to meet its end. The next thing that I did was to define the acceleration, which is the change in the velocity with respect to time. And I did the same sort of algebra with that equation and arrived at equation v is equal to v0 plus a times t. And I expressed a particular affection for this equation because I can use that equation to solve problems, and I will use it all throughout my physics. It has its limitations, but it's a very excellent equation that I can use to solve a large number of problems. So now that I have all of these definitions that describe the motion of objects in my universe, in the context of position, velocity, and acceleration, I can describe how things are moving about in the universe. I now would like to go out and solve some problems, right? So I've come to the end of inventing new information or new ideas of my description. I now want to look at how can I use my description of the universe to solve practical problems and make predictions about position, velocity, and acceleration in certain practical situations. So in order to do that, I'm going to do what is known in physics, well, in all of science really, as a derivation, a mathematical manipulation that demonstrates a new relationship from among relationships that are pre-existing. The shorthand of that is, I'm going to take these equations that I have over here, and I'm going to smash them together and make new equations out of them. The new equations are of more practical value. They're more useful to me. And so those will be the equations that I keep, and believe it or not, I'll discard the rest of this, except for v is equal to v0 plus at. I love that equation very much. So here's where I begin. I decide that for our honors physics course, we're going to only solve problems where the acceleration is constant. I already made that decision yesterday when I said that defining the acceleration as the rate of change of velocity was as far as I would go. That in our course of physics, I wouldn't say that the acceleration changes. So I'm going to begin with a certain assumption, and that assumption for our course that will hold for the entire course is that the acceleration is a constant. So our value for the acceleration, lowercase a is the acceleration, is a constant in all of the problems that we solve. That is not an assumption that we make when we study AP physics. In AP physics, we allow the acceleration to change. The reason why I'm holding back is that when you allow the acceleration to change, the math becomes more complicated. When you allow the acceleration to change, that is when calculus is required to solve physics problems. Let's lay off the calculus for the time being, shall we? And you can engage that in a higher level of physics if you choose to do that. So I'm going to choose only to solve problems where the acceleration is constant. Good news is there are a lot of situations in nature and in our everyday lives where the acceleration is at least approximately constant. So being able to solve problems of constant acceleration is a handy thing to be able to do. So I'm going to begin with a little experiment to investigate what constant acceleration looks like, and you'll find it familiar. If I make a graph of velocity as a function of time, and I start with an initial velocity, a graph of motion with constant acceleration would look like this, perhaps. The slope of the graph that I've drawn here is positive. It could just as well be negative. But the important thing is, since I realize that the slope of the velocity time graph is acceleration, this graph has a constant slope, which means it represents motion with constant acceleration. The reason why that matters to me here is that I want to make an important observation. If I make a measurement of the initial velocity and then make a measurement of the velocity sometime later, I have a habit of making a claim here that I don't know what happened in between. Well, in this case, I do. Since I've assumed that the acceleration is constant, then I know that what happened in between was that the velocity increased by equal amounts in equal intervals of time. Because acceleration is the number of meters per second. And if it's constant, then I add the same number of meters per second in every second. It increases in a linear way. That's why it looks like a line on the graph. This leads me to an observation that's useful to me in the demonstration I'm about to do. And the observation is this. If I wanted to, under these circumstances, calculate the average velocity can be calculated as the final velocity plus the initial velocity divided by 2. The final velocity plus the initial velocity divided by 2. That's what the average velocity is equal to. And you sort of knew that already because you know that in order to calculate an average of a thing, you add up the values of all the things and divide by the number of things. Well, here I only have 2 things, the initial velocity and the final velocity. Adding them and dividing by 2 gives me the average velocity. Only when the acceleration is constant. For example, imagine I give a test in here and everybody in the room takes the test. I can calculate the average grade on the test by adding up all the scores and dividing by the number of scores. That's how you calculate an average. But if I gave a test in such a way that this group here, the test was out of 80 points, and this group here, the test was out of 90 points, and this group here, the test was out of 100 points, I could not add together all those scores and divide by the number of scores to get the average, because for each individual test, the value per point is different. So this trick that I'm doing is only going to work when the acceleration is constant. So I'm cheating a little bit. I'm making an assumption. I'm limiting the physics that I can describe, but I'm doing that because we don't want to rush into crazy sophisticated math. So here I go. My goal is to create 2 new equations that'll be useful for solving problems. I'm going to begin with the equation that is ultimately going to be replaced. X is equal to x0 plus v average times t. I'm going to take this equation and smash it together with my other definitions, and when I'm done, I will have a final equation that is not obvious. You would not have guessed it. I wouldn't have been shocked if somebody had guessed that this equation, x is equal to x0 plus v average times t, was true. That would not have shocked me. But as I mix things together, things get a little bit more sophisticated, so I'm going to find something that may not be obvious. Here's how I proceed. I'm going to take the average velocity here and replace it with what I just claimed the average velocity is, v plus v0 divided by 2. So I'm going to rewrite the equation, x is equal to x0 plus v0 divided by 2, then multiplied by t. Now you may look at that and say, well, you've just made that equation worse. Well, got to break some eggs in order to make this particular omelet. Divided by 2. I've taken v average here and replaced it with what I know v average to be equal to, v plus v0 divided by 2. Looking in this equation, do you see the v that appears there? V. That is not the average velocity. That's the final velocity that appears there in this equation. Well, I've got an equation over here that says that the final velocity is equal to the initial velocity plus at. I'm going to replace that final velocity with this initial velocity. You may start to feel that I've lost my mind here a little bit, and that what I'm doing might not really have any practical value, but it really does. This v here, I'm going to replace it with v0 plus a times t, and then there's a plus a v0 on the end of it, and the whole works is divided by 2, and on the outside, the whole works is multiplied by t. Scheidly, please stop. It's okay, I'm almost done. This t and this t, they're both in the numerator. They would never cancel. And even if one was in the denominator, the answer would be no, they do not. This is messy. Look what I have here. I have a v0, and then later on along the numerator here, I have a plus v0. That's 2 v0s, right? So I could write that as 2 v0s, and then I have an at left over, but that's divided by 2. So I'm going to write in an intermediate step here a little bit of combination of things that I have. This is actually 2 v0 divided by 2 plus at divided by 2 times t. I'm using my considerable algebraic skill in order to get these results. Yeah, absolutely. I just included it in this step so that you would see, and you're exactly right, that this 2 in the numerator cancels the 2 in the denominator. Now I'm simply going to distribute the t, take a deep breath, and realize I have arrived at my final destination. The final position is equal to the initial position plus the initial velocity times t, because I've distributed the t to that term, plus 1/2 of the acceleration multiplied by t squared, where the t has become squared because I distributed the t. This equation, you can tell by looking at it, is a more refined version of x is equal to x0 plus v average times t. It's a more sophisticated version. It's a better version, which is why I'm going to jettison this equation after today and stick with this new version, x is equal to x0 plus v0 t plus 1/2 at squared. You should memorize it. It should be available to you at a moment's notice. It is dimensionally consistent because position is in meters, initial position in meters, velocity in meters per second multiplied by time in seconds, plus 1/2 doesn't have any units, meters per second squared multiplied by seconds squared. Meters plus meters plus meters plus meters plus meters, apples, apples, apples. A dimensionally consistent equation. Hopefully that will help you remember how the equation should be written out. That's one. I wanted two, so I'll do another demonstration. And this second demonstration, I'll start from the same place. X is equal to x0 plus v average times t. I'm going to start at the same place. And I'm going to take the same first step. My first step is to take the average velocity and write in what I know the average velocity is equal to, which is v plus v0 divided by 2, then multiplied by t. But now I'm going to go off in a different direction. Realize that acceleration is equal to delta v divided by t. That's by definition. Acceleration is delta v divided by delta t. So I could do some algebra to this and realize from that t is equal to delta v divided by a. Just a little bit of algebraic reorganization. So what I'm going to do is replace t in this equation with delta v over a. And when I do that, I'm going to write in what I know delta v to be equal to. Like any change quantity, delta v is the final velocity minus the initial velocity. So I'm going to write this way. The final velocity minus the initial velocity divided by a is what the time is equal to. Oh, messy, messy. I'm multiplying these two slightly daunting fractions. When I multiply fractions, I multiply their numerators and I multiply the denominators. When I multiply the denominators here, I get 2a. So I'm going to write it this way, a little bit quirky, but it serves my purposes. I'm going to write this as 1 over 2a, v plus v0 times v minus v. Oh, doesn't it just make you want to foil? Yeah, the urge to foil. So let's go ahead and do that. Before I do, you see I have x is equal to x0 plus this term here. If I subtract x0 to the other side of the equation, then the left-hand side of the equation becomes x minus x0, which of course is delta x. And if I multiply the 2a over to join it, here on the left-hand side I have 2a times delta x is equal to v plus v0 times v minus v0. So now I see that I'm going to FOIL this, and I'll do it without distraction. FOILing this out, what do I get? Well, I get v squared minus v0 plus v0 plus v0 squared. I'm sorry, minus v0 squared. My bad. But in that FOIL, these cross terms, v0 and v0, they cancel each other. I have one here is negative, one here is positive. So the cross terms cancel each other out. And what I'm left with is that 2a delta x is equal to v squared minus v0 squared, and I get something that is not at all obvious. And that is that the final velocity squared is equal to the initial velocity squared plus twice the acceleration multiplied by the displacement. Never ever would have guessed that was true, and yet it is. In the case of motion with constant acceleration, both of these equations, x is equal to x0 plus v₀t plus 1/2 at squared, and again, v squared is equal to v0 squared plus 2a delta x, both of these equations are true, and they have value. Out of these three equations that appear here in boxes, v is equal to v0 plus at allows me to predict the future of the velocity. That's tremendous. X is equal to x0 plus v₀t plus 1/2 at squared is a more sophisticated version of x is equal to x0 plus v average times t. So I welcome the added sophistication because I can solve more interesting problems. And this additional equation, this bonus equation, is extraordinarily useful to me for solving problems when the time is not given. Notice that the equation v squared is equal to v0 squared plus 2a delta x does not have time in it. Not explicitly anyway. And so I can solve problems where the time is not given using this equation. These three equations, which are true when the acceleration is constant, are known as the kinematic equation in physics, and their application of the solution of problems is kinematic.